Okay, guys, I think I had some issues in the last 15-20 minutes of the section 2.7. So I think that happened for good because that video I felt too long. So there are still one or two little bit complicated examples I'm going to talk about in section 2.7. That is the combinations. So I'll make this as a really small video, say 15 minutes per se, on just one or two couple more examples on combinations, which I feel they're a little bit complicated. And then I'll upload both the videos at the same time. Okay, so let us start working on a little bit more complicated examples on combinations. Okay, I don't think I'm sharing this here. Let's open this. Okay, let us share this. Okay, share application. Okay, I got it. Apologize for the wait. Okay, let us look at the complicated examples. Just now I mentioned uh, permutations means order does not matter. Combinations means order does matter. Okay, let us come back to at least almost all the applications and problems. I think you use combinations more than the permutations. So let us look into this. There are 7 women and 5 men in a department. That means there are total 12 people, and 7 of them were women and 5 of them were men. And how many ways you can select 4 people? Again, we are not specifying men or women, so you're selecting 4 people out of 12. So here the order really doesn't matter because you're not filling up any spot. So you can write your answer as E12, 4 or 12 C4, whatever you'll write it. It doesn't matter. Okay, that's your answer. In how many ways you can select this committee? When I say this committee, that means the committee should have 4 people, but you should have 2 women and 2 men. That means 2 people should come from here and 2 people should come from here. So and means multiplying. So if you know how the number of ways you can do this job times this job, you're done. So the number of ways you can select 2 people out of 7 people here by itself, you know, the order is doesn't matter. That can be done in 7C2 ways, and the second one can be done in 5C2 ways. So that is your answer. Again, sometimes you can write like this as well. Again, in the exam or in the, it doesn't matter to me. You don't need to simplify this or anything like that. And now, how many ways this committee means you need to select a committee of 4 people. There must be at least 2 women. When I use the word at least 2 women, that means 2 women or 3 women or all the 4 can be women. Or means you're adding. If you know how to do this job plus this, then you're done. But please remember the one thing here you need to understand. If you are selecting 2 women, means the other 2 should be men. That you need to understand. If you are selecting 3 women, means the other one should be men. If you are selecting 4 women, means 0 men. So you need to know how many ways you can do this job plus this plus this. How many ways you can do this? That can be done in this many ways that you had done before. Plus, how many ways I can select this? 7C3 times 5C1 with the same logic as above. Plus 7C4. You can put 5C0, but that is same as 1. So you can leave your answer like this. Okay. So that the thing is, when you select 2 women, the other 2 should be men. Let us go to one more example. How many 8-letter words are possible with no repeated letters can be constructed using 26? That means you are selecting a 8-letter word, 1, 2, 3, 4, 5, 6, 7, 8. Okay, let us consider first 2 vowels. Okay, and among the 8, the 2 of them should be vowels, and there are total 5 vowels, A, E, I, O, U. How many 8-letter words are formed with 2 vowels? That means you need to understand the rest of the 6 are consonants. How many ways you can do that? There are total 5 vowels, right? A, I, O, U. The number of ways I can do that is 5C2 ways. And the rest of the 6 has to be consonants. How many consonants are there? 21. So that can be done in 21 6 ways. Right, so this is going to give you the number of 8-letter words are possible. Here, order really doesn't matter, right, at this point. But you need to understand one thing with exactly 2 vowels and 6 consonants. For example, this is one word, A, E, B, C, D, E, J, for example. Not E, I guess. E is a consonant, so let us make it as Y. A, E, B, C, D, Y, J. This is a word, okay? Again, it might not have any meaning, but this is a word with exactly 2 vowels and the rest of them are consonants. If I change this order and I can write that as E, A, B, C, D, Y, J. This is another 8-letter word, completely different from this because I changed the order. So you need to count in how many ways these 8 can rearrange among themselves. That can be done in 8 factorial ways. So the number of 8-letter words with 2 vowels and 6 consonants is this, because this is all the 8-letter words with 2 vowels and 6 consonants, and these 8 factorial is how each word can rearrange among themselves. Or 3 vowels means R means plus, so with the same logic, 5C3 times 21C5 and 8 factorial. 4 vowels is 5C4 with the same logic. Now the last, the 5 vowels is going to be 5C5 21 3. The rest of the 3 should be consonants, and the number of ways they can arrange among themselves is 8 factorial. So this entire thing should be your answer. So your answer should be this plus this plus this plus this. That should be your answer. You don't need to simplify. You know how difficult that is. So in the exam or in the assignment, please leave it like this. Okay, I think these are the complicated examples I want to go through. So I just want to state 2 results. Again, I'm going to give you very informal proofs for one, and for the other I'll point where you can read the proof in the book. So let us look into this small, nice, cute result. This is C of n r is same as C of n comma n minus r. What this says is the number of ways I can pick r things out of n things is exactly same as the number of ways I can pick n minus r things out of n things. Let us look by an example. C of 5, 3. That's what this is saying. If n equals to 5 and r equals to 3, for example. And this is saying 5 minus 3. That means this is 5C2. These two should be same. That's what that is saying. Let us look into this. By the definition, this is n factorial or r factorial. This that is what this is. Now let us calculate this. And this is 5 minus 2 is 3 factorial. So you see both are equal. So all this is saying is, just imagine this, okay? For example, there are 5 apples, and among those 5, say 3 of them are red apples and 2 of them are green apples. So C5, C3 says the number of ways I can pick 3 red apples out of 5. If you pick, suppose 3 red apples, whatever is left behind those 2 red through green apples. That means picking 3 red apples out of 5 is exactly same as picking 2 green apples, because those are the only things left behind. If you are picking them, that means you are picking the you are selecting to leave the other 2 as well. That is what it is saying. So that is what the combinatorial proof. So if you select r things out of n things, that is C of n comma r, this is a number of ways of selecting r items out of n items. Once you select n items, sorry, once you select r items out of n, the remaining r are left behind, right? The remaining n minus 1 r are left behind. Again, if you want a little bit more explanation, please go to the page number say 36 on the textbook. So the remaining n minus r are left behind. That means so selecting r things is equals to the number of ways of selecting r things is equals to the number of ways of, I think I need to share this again, guys. I think I apologize. Let's share this again. Share application. Man. Cancel share application. I apologize, guys, if there is any gap in the video. So C of n are ways of selecting r items. So once you select, the remaining n minus r are left behind. So the number of ways of selecting r things is the number of ways of leaving n minus r things. That is as simple as that. So that is the reason C of n r equals to C of n times n minus r. This is, again, I have given you a little bit of a vague proof because combinatorial proof depends mainly on counting techniques. But the proof which makes more sense is the algebraic proof, which I'm going to do it right here. So this is what you are trying to prove. Let us calculate the left hand side. C of n r is by definition this. Now if I want to calculate this, let us change the color for the sake of it. By definition, this is n factorial over n minus r factorial divided by, just by definition. In place of r, you have n minus r. So by formula, in place of r, you have to put n minus r. That's what I did. So if you simplify this, n minus n will cancel out and I'll get r factorial. And you saw that these two are equal. So this is more algebraic proof, which makes more sense. So I calculated the left hand side and showed that is exactly same as the right hand side. Now the next result, I am going to state it without any proof, but I strongly recommend, this is theorem 2.2. This is on page 36 of the textbook. They have given both combinatorial proof and algebraic proof in the textbook. So please read. But I will explain this with the help of an example. Again, it is it's not very difficult, frankly. So for example, take n equals to 5 and r equals to 3. This is just an example. So this is simply saying C of 5, 3 is equals to n minus 1 is 4, r minus 1 is 2, n minus 1 is 4, and r is 3. So calculate this side and this side, it is saying they're equal. Just follow the definition. This is simply this. And this is simply this. 4 minus 2 factorial. And this is simply this. I just used the definition. So 5 factorial over 3 factorial 2 1 factorial. So this is 5 times 4 times 3 times 2 times 1 over this will cancel out, and 2 2s are 4, so this side I got 10. Now let us look into this. 4 times 3 times these two will cancel out. 2 2s are 4, that is going to be 6. Let us look into this. 1 factorial is 1, right? So this is 4. So yeah, we are done. Again, I proved this with the help of an example, but I strongly recommend please read the proof on page 36. Once again, I apologize. The previous thing, I thought I was sharing this. Suddenly, somehow the internet connection screwed up. So I am forced to do one more presentation. Even when I am doing this in the middle, suddenly you might see a PowerPoint might have vanished in the middle, but again I shared it back. So hopefully there is no lag or anything. So thank you very much for your patience. So I think this is a bit bad time I picked because of the internet issues. So again, read the proof on page 36. Again, in a nutshell, permutations means order important, combinations means order not important. So I'm going to post an assignment on these sections. So at this point of time, I think I am done here. So let us, okay, save this. Okay, I think we are done here. I'm going to stop the recording now.